So before we get on with today's lecture, I just want to point out a couple of people who actually make this happen. The only thing I do is show up and have a donut and come down here in the front. The people who really make it happen are actually standing in the back of the room. First of all, the brains behind the operation. Inga Karliner is right there. She's the one who really pulls all this together and makes the Saturday program happen. We really appreciate all the work that she does. And I've been upstaged by guys. Not to be outdone, the person who's doing all the organizational work that you probably saw out front as you came in is the person who's taking care of all of this, and that's Tony Pitt. She's back there in the back of the room. All of the neat demonstrations you're going to see this fall are done courtesy of or through a lot of contribution from Marion Evans, who's right there, and Gwendolyn Smith, who you'll see coming in and out of the back of the room. They do a great job. So let's go on with today's program. In fact, I can just take this part down and introduce Sue Kieffer, who's here to tell us about steaming geysers and puffing volcanoes. Sue has a background in physics, mathematics, planetary science, and geology. She has her PhD from Caltech University. We were fortunate to get her here at the University of Illinois in 2002, where she is the Walgreen Chair and Professor of Geology. She's won more awards than I can list in a half an hour, so I'm not going to try. Let me just list a couple of the highlights. MacArthur Fellowship, Sloan Fellowship, Fellow of the American Academy of Arts and Sciences, and the list goes on and on. That was just to give you an idea. She's also a very gifted teacher, and she's done a lot of outreach to help underprivileged high school students learn about math and science. And it's a real privilege to have her here today to tell us about geology of geysers and volcanoes. Please join me in welcoming Sue Kieffer.
Thank you all for coming. Like me, you're missing the farmer's market this morning, so that's a real sacrifice because I enjoy that event. I want to thank the physics department for the help that they've given me. All of this got set up without my even noticing it. And got a couple helpers here that are going to hopefully get me through this multimedia presentation. I've got videos, and we've got the demos here, and of course PowerPoint. Does this come up?
Here we go.
There we go. I started studying geysers in 1976, thinking I'd have a 5-year plan to learn how geysers work so that I could apply it to volcanoes, which are much more complicated. And I'm now in the 30th year, or 28th year of a 5-year plan. And I keep learning more and more about geysers as I ask questions. I'm going to start by talking about Old Faithful Geyser in Yellowstone National Park. A geyser is basically a pot of hot water that intermittently bursts forth, and that's what the word Gosha meant in Icelandic when geysers were first named after a great geyser in Iceland. And you'll see this geyser here intermittently bursts forth. It's heated at the bottom, and when it gets hot enough for steam to form in the bottom, it pushes the plug of water off the top. This is a famous chemist named Bunsen came up with this idea. When the water comes out the top, it cools down and falls back in to the pan and has to go down and get reheated. So that's a simple geyser. Old Faithful is actually much more complicated than that. And I started studying Old Faithful because it's so predictable that you can actually do science. And we knew that we could get into the conduit. And so I studied it a variety of different ways, and it's turned out over 30 years to be a very relevant study because Old Faithful's intervals are getting longer and longer, and the question's constantly being asked, is Old Faithful dying? And eventually it will. If you look carefully around the area of Old Faithful, you see about 3 or 4 mounds that look like this, which are extinct Old Faithfuls. And this little knob here is a petrified tree stump, and that's been dated at about 350 years. So Old Faithful's been around, maybe around a couple hundred more years, or depending on earthquake activity, maybe not that long. weeks, my geyser.com site will be active. We're moving it to a different server, and you can log on, and we wrote an electronic book that was kind of fun about Old Faithful. I've owned geyser.com basically since the .com industry started. I've been offered a substantial amount of money for it and refused, by a bottled water company. I've refused to sell it. So I'm going to show you a video, parts of a video that we took. My colleague Jim Westfall at Caltech is one of the most clever experimentalists, and I had done a lot of work. Jim and I, in 1980s, put a pressure temperature probe into Old Faithful, and when miniature video cameras came out in the early 90s, we built a camera to lower into the geyser. Now this is not trivial, because we're going down through steam, 93-degree steam, which is the boiling temperature of water. So we had to insulate the camera with ice, but then we had to heat the lens so that the steam would condense on the lens, and then we had to provide our own illumination. So basically Rick Hutchinson and I were up at the vent, lowering the probe. Jim was in a little tent, a little pup tent off to the side, doing the illumination. So what you're seeing is actually a scientific video. It's not a Hollywood production. So I'm going to start, I have to switch video after a couple of minutes, but I'm going to start, show you the instrument, and then I'll switch the video and take you down on a descent into the geyser. I didn't get it on it. It's not switching. Oh, I'm hit video instead of VCR. Okay. Whoops, all right. Faithful. That was well timed. I got to choose the music. And my colleague Jim, who you'll see, narrates this. Yeah, good to have the lights off.
As you're watching Old Faithful for the last few minutes before an eruption, we would like to tell you a bit about this video. A small group of scientists from the California Institute of Technology, Arizona State University, and Yellowstone National Park have been studying how Old Faithful works in detail. We are especially interested in geysers since they seem to work in very similar ways to volcanoes, like Mount St. Helens, yet we can safely work around Old Faithful. Some time ago, we made measurements of temperature and pressure at several depths down the bed of Old Faithful. We collected data starting from the time that it emptied out at the end of an eruption until it refilled and finally erupted again. In this work, we learned many details of how geysers work. But of course, we still have many questions. We'd like to know where the water comes from. Does it come from the sides or from the bottom or both? Why does it stop filling up at about 15 feet below the top? If you look down from the top, the vent is a slot about 4 or 5 feet long and about a foot wide. You can see down about 10 feet. But below that, we really don't have any idea what the vent looks like, or what effect its shape may have on the way Old Faithful erupts. We wonder if the vent fills with water quietly, or if it is boiling. Old Faithful also makes a series of big splashes before each eruption. You have been seeing these in the video. In fact, an especially large one usually triggers off the eruption. We don't really understand what that's all about. These and many other questions have led us to want to see what's down there. Just recently, it's been possible to get a very small television camera. We have put one of these cameras in a metal housing to protect it from the boiling water and to keep it cool. With it, we have been taking video pictures down into the throat of Old Faithful. We thought you might like to see them. As Old Faithful again throws a big bunch of water out, this time it probably is going to start the eruption. And indeed that's the case. There is Old Faithful in full eruption. Here you see that Old Faithful's surface vent is a slot-like structure, as I mentioned before. It's covered with a material called cinder, which looks kind of like snow, but it's actually made out of silica, a very hard material that coats everything that gets splashed with the erupted water. The housing we built for the camera is seen in this view. It's a stainless steel thermos bottle with the camera on the inside cooled with ice. It's attached to the surface by a long cable. You can see the white 1-foot markers on the cable. Here we are testing the lights needed to take video pictures down the dark vent. Here's the little camera itself out of the housing. It's about 2 inches long and about 3/4 of an inch in diameter, lines and hole. We now have the camera down into the...
There's a cute story about those white gloves. Jim was walking around Caltech looking for a secretary with beautiful hands to hold this, because he's got gnarled hands from being an experimentalist, and he realized it wasn't politically correct to go searching for a woman with beautiful hands. And so he put on the photographer's gloves so that his hands wouldn't show. Okay, we've gone down the conduit a number of times, and this video shows two descents of ascents. So I'm going to start it now when we've come up from the first ascent and show you about 5 minutes of the second ascent here, or descent and ascent. So down we go into a big
up and down, and of course when we got close to the wall, then we had to turn the lights down to keep from overexposing the video, and then as we got out into the big open areas, we had to turn them on more intensely. We didn't do that very perfectly. Notice, by the way, in the bottom right-hand corner, you can see a waterfall falling down the side. Seems to be coming from kind of in underneath this slot.
started a little way, so we're
It's
still
not
coming
very
up
much
from the
water,
first.
so we don't think that that's a major source of the water that's filling the vent. Now we're back up into really quite a fairly narrow slot, and we seem to have gotten up above so much splashing and other things. However, occasionally, as just in, you see fog. That's because the wind is gradually getting a little higher up at the top, and it's blowing down into the vent, and that allows fog to form as it cools the steam in the vent. And you will see that occasionally as we go along when a gust of wind causes some air to get down in the vent. The vent is full only of steam normally, and the steam is quite clear, fortunately, otherwise we wouldn't be able to see it, because everything is at the boiling temperature of the water, so
That's what we hope
Don't
doesn't
get it.
happen when we have the camera.
fog of steam as you do out of a chimney or something like that. Big blast of water right then coming from down below, continuing at some level here. It gets onto the window of the camera,
That's not that we have to go through is 4
makes
inches
the
of
image
diameter.
a little bit fuzzy. There's another blast of air. We've stopped now, we're about 11 feet, and we've stopped now to decide what we are going to do, whether we're going to give up at this point, thinking that we're lucky and we didn't bust our camera, or decide whether we want to get brave and go back down again and see, now that we understand better what's going on, see a little more details about that. And so we decided, in fact, to go back down again. We have an awful lot of nice video there, and if somehow we do the camera in this process, well, we try it. And we have a lot of information to keep us busy for quite some time. So now that we kind of know what to expect, we'll see and recognize things better than we did the first time down. Notice how very smooth the walls are. That's the center coating everything. There's our waterfall again, really quite striking in the right-hand side of the picture. But really, there's not very much water in that. And you can see there's a little puddle in the lights. And now we can already see the top of the boiling water. It's coming very much higher up into the vent than it was when we were down just a few minutes ago. We've come to our little shelf again, and the first of the little shelves, and we bang around on it again, and
difference.
Notice though that there's lots of water boiling around, it's turning the camera around. There's our shelf where we got stuck last time, and we have to worry about whether it's going to get stuck again. And sure enough, we do. The camera is now not moving. But then suddenly something happens, probably a big splash of water from the wild boiling, and kind of knocks us off of the shelf. And now we've gone down a little ways, and we really are seeing the wildly boiling water and water pouring around us in all directions. Looks like a tornado now and again as it twists the camera, spins the camera around on the end of its cable. We really became very concerned whether our cameras could survive all of this. It certainly wasn't made with that in mind. Never had any idea that we were going to be involved in anything so wild as this. Notice the big blast of water from the sidewall at that time. That was a lot of water, but it was just a sudden burst. So we don't really know whether that's one of the sources of water propelling it that somehow doesn't run in a steady way, or whether it's just water that's splashed over the edge and kind of off to the side and is now running back in. We're coming back up again slowly, coming up a foot and waiting 2 or 3 seconds, and then another foot. And every once in a while we get this completely drowned in water and foam, and you can't see anything at all. We're coming up again now on the little shelf, and notice how much water is running down the side of it now. Clearly just from the splashing of the water in the wild boiling. Things really are getting very much wilder as we are down there this time. The vent is clearly filling up with water. We're still about 20 or 25 minutes before the next eruption. So we're not concerned that we're going to suddenly get caught in an eruption. I'm sure the camera would not survive. So what have we learned? We didn't see an obvious large source of water, so we think it must be coming from below 40 feet somewhere. We also saw no side channel that would explain why the vent doesn't fill up above 15 feet. We'll need to watch what happens when the water level actually reaches that depth to understand what's happening there, I think. We saw that the vent continues as a slot down to about 35 feet and then opens up to a bigger shape, and that helps us understand somewhat how the eruption works. We found the filling process is certainly not a common activity, and we now understand the pre-eruption splashes. They're just the top of the widely boiling waters that nears the surface. Clearly there's much to be learned using this downhole camera. We hope you enjoyed looking down into Old Faithful with us, and we'd like to thank the folks from the Yellowstone National Park for permission to put our camera in Old Faithful and for assistance in doing so.
Well, I find out on Monday whether I get permission to put another probe down this year. The Park Service has gotten very conservative about this, but they're also concerned that Old Faithful's a national and international icon, and if its intervals are slowing down, and they've got millions and hundreds of millions of dollars of investment in the Old Faithful area, they need to do some long-range planning. So we'll see what happens then. Well, I understand that there's some people here from a statistics class, so I threw in one slide. I have collected 6 years of data. I pushed the right buttons. Oh, rocks. Maybe the computer went to sleep. That's it. This is 6 years of data. It's a 94% complete. We had infrared sensors in the winter, and at night. And Old Faithful has two modes of eruption. If you look here, this is intervals. It has short intervals and long intervals. And I just put up the statistics. The short interval mean is 56 minutes. The long mean is 84 minutes. The standard deviations are here. And about a third of the intervals of eruptions are short. Short eruptions followed by a short interval, and a long eruption by a long interval. Well, I want to move on to smoke rings. Now, there's a reason I started studying smoke rings, and I'll get to that later. This is a smoke ring from Mount Etna. And these rings are often 1 to 2 football fields in diameter. They're enormous. And nobody really knows how volcanoes blow smoke rings. But you can see here, I've pulled as many as I could off the web. This is Mount Etna. Here's 2 smoke rings. There's a little one, leaves a trail of vapor. And they actually aren't smoke, they're steam. And it's quite remarkable that these things will last for up to 10 minutes in cold air made out of steam. And we're going to show you how smoke rings work. My crew here. Let's see. There's a couple more. And he's got the best aim for blowing out this candle with a smoke ring. So, the smoke ring's going to come out of this hole. These are great. You see how far? Do you think you can blow one that far? Are you going to blow out the candle now?
We'll try that. Maybe I'll use the big one.
Oh. Well, somehow volcanoes are doing that. And this one had a crazy trajectory, spinning around, and it still didn't break up. And it turned out the Earth was thought friction. These smoke rings could break up. But in the 1970s, at MIT discovered instability on the smoke ring, instability now, that will always cause them to break up, even if there's no friction around. And this is, Etna is not unique, but it's certainly the most common smoke ring blower. This is also a volcano in Japan blowing one, not a very good one, Stromboli. And it turns out dolphins are master blowers of smoke rings, except air rings. And they blow them and they play with them, and they can even use their flippers to keep them from rising to the surface. They bat them around. So here's, you can go on the web and just look for smoke rings and find out this is the demonstration you saw. This is called fog rings. And when you put a puff of air out through a slot, the air on the edges is dragging a little bit. And so it causes it to curl up. And this is called a vortex. And it's just like a tornado. If you can imagine you are looking down on a tornado or Hurricane Ivan, there's the eye of it. That's a lower pressure region. It traps the fog or the smoke in there, and as it travels, and that's what keeps it, it's wrapped in there. So whatever that geometry is at Mount Etna, on the scale of 100 or 200 meters, it's blowing a smoke ring out, and the friction on the edges of maybe a crater in there or something is wrapping this around, and things will propagate for as much as 10 minutes. Well, the reason I got interested in smoke rings was because of a colleague who came back, and the rat's sitting back there, and piqued my curiosity. I have never seen, and after probably 50 hours on the web, I have never seen a volcano that has this kind of scallop structure. And so it's all around here. This is a volcano called Reventador. And I was just intrigued by this because I just didn't understand it. I guess that's what science is about. And I've been collecting pictures. The web is just a marvelous resource. I wish I were a student again because there's so much out there. This is a digital image of this volcano Reventador. It's actually over about the last 300 million years. The first stage isn't visible anymore. The second stage is this big edifice here. And I think about 50,000 years ago, the summit of that collapsed, and the new volcano Reventador is right here. the part of it. This volcano is very near the capital of Ecuador, a city called Quito. And during this eruption, Quito was blanketed with ash. The air closed for 3 days because if this ash gets into jet aircraft engines, it melts and they stall. And actually, British Airways almost lost a plane in Alaska. So there's now part of weather forecasts for aviation include volcanic ash trajectories because you can't always see the volcanic ash. And after this eruption, the residents of Quito were on a mandatory broom sweeping out ash out of the city. Well, in November of 2002, Reventador woke up after, I think, about 50 years of being asleep and started an eruption. And this was like a big eruption of Old Faithful. It was very steam-rich, sent an eruption plume rising. And that plume rose and spread out, and I'm going to show you some more clouds like this. It rises till it's just neutral buoyancy and then spreads out radially. And in this day, there was no wind, which was really neat, so it just spread out. And notice how white this eruption is. Now at the base, a pyroclastic flow erupted, coming down the slopes here. And the only oil pipeline in Ecuador goes very close to this volcano. And in fact, this and here's the pipeline. I don't know why these guys are standing and taking pictures because this pipeline actually was moved about 3 feet by the ash flows that got to it. How dark it is compared to this slide. As far as I've been able to reconstruct, and I've actually had to take some Spanish clips from the Ecuador Institute of Volcanology and put them in the AltaVista translator on the computer to find out the history of this. I think what happened was that right at this time, that whole cone collapsed. The little cone I told you about collapsed in and produced this very ugly cloud. And I don't know the time sequence. I think this is intriguing. It's a different photographer, but you can see the scallop structure. And here's the picture I showed you that we were so fascinated by. So I originally had the idea that this was a vortex head, like a smoke ring. It just isn't as clean in the eruption continuum. We talk about these starting vortex heads on volcanoes. So I thought, well, maybe this was the lignal instability. That was the hypothesis I had for about a month. But the more I researched these instabilities on the web, the more frustrated I got. And eventually I got into thinking, well, maybe it's a rising hot mass. Maybe there's some analogies to nuclear mushroom clouds. And I emailed Jeremiah Sullivan, who had some expertise in that. I've been through the physics department here, the atmospheric sciences department, the Caltech fluid mechanics department, trying to figure out what this structure is. And I couldn't find anything in the nuclear literature that really looked like this either, because those vortices go out and they curl around. They don't go up and down. This is another volcano. This volcano started erupting while Reventador was erupting, and it's not that far away from it, but they couldn't. And I thought, well, maybe there's a little bit of that scallop structure here, but it's certainly nothing that you would want to bet your life on. So here's the Mount Redoubt mushroom cloud. It just doesn't look the same. And so I found a convection cloud started. It was 170 in Texas, and this little bubble of hot air came up and it started a cloud, but there wasn't enough hot air to finish it. This is the closest I've come to finding a vortex sheet rolling up that might have a similar structure. And I'm going to let you judge. I've got it just repeated and turned upside down on another slide. Well, while I was searching the web, I stumbled across a howitzer. And this is my best guess as of yesterday, what we might be seeing at Reventador. This is called a muzzle brake on a howitzer. And it's designed so that when they fire the howitzer, the recoil doesn't go backward. They put a slotted liner on the top of it, and the gases come out the side, momentum radially, so they can fire again. And if this is the proper analogy, and I'll let you do some comparison of these two. Here, I've turned the three-dimensional vortex upside down. If this is the proper analogy, I'm thinking that this photographer was really lucky, and he captured the mushroom cloud before it really started spreading out, and that those scallops are a reflection of how that volcanic cone collapsed in sectors, and that we're really seeing the start of the eruption coming out through the fissures that developed. Now, unfortunately, this is geology. It's not physics or engineering, so I don't get to go in the lab and test my guess. I could go into the lab and build a little model and see if you get a vortex. That if you, instead of having that nice hole, if we put some teeth around it, what would our smoke ring look like? And I unfortunately only came up with this hypothesis yesterday, so I didn't have time to test this experiment. You can all, by the way, go home. Maybe you can test the experiment for me. You can make a smoke ring generator by just cutting a hole out of a can and putting a rubber on it, and you can blow out candles in your house just by playing with this. So that's what I'm going to spend my weekend doing. Okay, well, as you see, I've been studying geysers and I keep getting distracted by volcanoes. It turns out 3 years after I started my studies of Old Faithful, they discovered volcanoes on the satellite of Jupiter called Io. And I got pulled off my Old Faithful studies for a couple of years to look at these volcanoes on Io, which is now, we know it's the most volcanically active body in the solar system. There's volcanoes erupting all the time. And they can actually be seen as hotspots by telescopes on the Earth. Hubble Space Telescope's been monitoring them, and then the Galileo and Voyager spacecrafts. Well, 4 years after I started studying geysers, Mount St. Helens started erupting. And its initial eruptions were geyser-like. They were almost the same scale as Old Faithful. They were steam eruptions as magma moved up into the mountain and heated the groundwater in the mountain. And I went there with my trusty Super 8 camera, dying in hindsight to have had a small portable video, and filmed these eruptions and was trying to work the intervals back to figure out what the heat in the mountain was. And that was in March of 1980. In the middle of April, the mountain kind of dried up, but we were measuring the side of the volcano, the north flank, and it was moving out at 1 meter a day as magma was being intruded into the volcano. And on the morning of May 18th, the mountain collapsed. And I'm going to show you some of the slides from 2 eyewitnesses. The beginning of the eruption was captured by the Stoffels. Could we turn down the lights a little bit? They were flying in an airplane around the volcano, and they noticed that it looked like the volcano was sweating. It was very wet looking. And they noticed some ice falling down in here. And you can see here little avalanches occurring. And if you look at these pictures in detail, you can actually see a crack growing there and this ice field enlarging. And they concluded that it was an earthquake. And they were right. The earthquake, in fact, was associated with the complete collapse of the north flank. And they got these 3 pictures. You can see the flank starting to collapse here. There's a little puff of steam coming up there, another puff there. And at that point, they were in deep trouble because the material was coming out of the volcano toward the north. Sorry, we got these pictures too. Toward the north at 100 meters a second. Sorry, I don't know what that is in airplane speed. But they couldn't outfly it. And they made a lucky decision. They veered off to the east, and they were actually able to escape the cloud by getting out to the east. Because if they had tried to go to the north, they would have been overtaken by this cloud. Now, keep this little plume in mind, right here, because I'm going to switch to an observer named Keith Ronholm, who was miles to the northeast. And he got this beautiful, I guess this is a sunset picture. I put sunrise, but I think now this is west, so that would be sunset the night before. So he got up in the morning, took this picture, and then he saw the eruption starting. And that plume there is the same little plume that the Stoffels had photographed in their airplane. So they're up here somewhere trying to get out of this thing. And these pictures are a few seconds apart. Now at the time, we had the geologic record suggested that if you were on a ridge top, you were safe from these events because the deposits were all in the valleys. In hindsight, we know the deposits are in the valleys because they wash down the hills there, and you're not safe if you're on a ridge. About 4 ridges in front of him, so he thought he was still safe here. I've actually talked to him. This is an event called the lateral blast. And he got concerned when the ridges started disappearing. And took these pictures. These are what are called pileus clouds. It's moist air in the valley that's being lifted up by the heat, just like you can see around clouds on a humid day around here. And so he kept on shooting for a while, And then he decided he better get out of here. And he only escaped by getting in his car and driving, following the taillights of a logging truck that was ahead of him because the ash was falling on him. His windshield wipers eventually failed, but he got out to the northeast. Well, this blast eventually, this is a plume from the blast, and it eventually developed into the afternoon event. At noon, this Plinian eruption started that looks very much like the Reventador plume that I talked about. So the Reventador scenario started with a Plinian eruption like this, and then the summit collapsed. Mount St. Helens, the volcano collapsed, and then took 4 hours to clear out the vent and go into a Plinian eruption that lasted for a couple days here. So I went back to Mount St. Helens. I'd gone home and went back for the day, and this is a picture my students like. It's like I got set down by a helicopter, and I said, what happened? You know, there's nothing left. The trees here are all blown down. This is all the trees were taken out, and even the soil was stripped off. And this is actually the site where I had been camped in March, about 5 miles away from the volcano. And it's very close to where we lost our USGS observer who was monitoring the volcano. There were about 55 people killed. They were people who had disobeyed the hazard zone and were in there. This particular person, I think, was a National Geographic photographer. And you can see the blast was extremely strong. It moved these big pieces of lumbering equipment. I don't know how far because we didn't know where they started, but you can see the tree trunks in here that were flying around in this lateral blast. And if this had happened on a Monday instead of a Sunday, there would have been a lot more loss of life because Weyerhaeuser was continuing to harvest in here. They eventually salvaged all of the wood that was blown down. And there was a lot of it. There was, I think, 1 billion board feet. So in this zone, all the trees were stripped out and the flow just went radial away from the volcano. There were 3,000-foot valleys in there, and it just went right across them. It didn't get deflected down. Further out, the tree stumps were left, but the trees were gone. And these tree stumps were good indicators of the direction that the blast went. And then here you can see the trees. They have root balls, but no limbs. They're like asparagus. The top snapped off and the limbs are gone. Well, I was out in the field. I just had no clue what happened. I couldn't explain what I saw. And I went back to the office in Flagstaff and spent a few months mapping in detail the directions of the blown down trees. And I'm not going to show you the details, but I defined 3 different zones of devastation north of the volcano. So this is if you were looking down on the volcano, which is here. The north flank that collapsed is here with the X. Keith Ronholm was just out in this region, and he was able to escape out this way. The Stoffels had been flying around, and they escaped that way. In this red zone, the trees just went out from the volcano, and the blast didn't go down this Toutle River Valley, which was huge. It wrapped around the volcano. Actually, the blast went south of an east-west line. And then when it got further out, I call this the direct blast zone. When the blast got further out, it started losing energy, and it started following the river valleys, and I call that the channelized blast zone. And then further out, where the yellow is, enough of the dust fell out that the blast became buoyant. It lifted off the ground and just singed the trees underneath it. And it's really neat because where the topography was going uphill, it had more trouble lifting off, and so you have a wide zone, and where the topography was going down, it lifted off faster, and you have a narrow singed zone. So that was understandable. What I'm going to argue was that this area, in the red zone, gravity wasn't important in the momentum equation. But when you got out here, in the channelized blast zone, gravity became a dominant force driving the flows down the valleys. Well, I had to learn rocket nozzle theory because my hypothesis was that when the mountainside fell away, material, steam that was in there at 150 times atmospheric pressure suddenly was exposed to the atmosphere. And it just expanded out, like if you punch a hole in the boiler. And that flow is called compressible flow. It's studied largely by the aeronautical engineering community. And so I had to start learning rocket dynamics back in the 1980s. It's not something a geologist grows up with. And I can show you a little sketch of what goes on inside of the plume from a rocket. like a Saturn V. And the gases in the rocket, or in this case for Mount St. Helens, come out of the vent, so pretend you're looking down on the mountain or down on a cross-section of a rocket nozzle, and they expand out to the sides because they're at higher pressure than the atmospheric pressure. And so they expand laterally and straight ahead. And they're trying to get back to match the boundary condition at atmospheric pressure. But it's a nonlinear process, and so it actually overexpands and goes back and forth in detail. It expands through here and eventually overshoots, and you get a shock wave sitting inside the flow. And this shock, if it passes over you, makes an audible boom. Or if you were trapped in it, you would feel a velocity change and a pressure change. So I did some calculations for conditions I thought were appropriate to Mount St. Helens. And this now is my little model that I did in 1980. And we're actually using a big code from the Rocket Center here on campus to try to now do the simulation with modern supercomputers. And so you're looking down, again, at a map of an expanding, of the pressure and velocity conditions in an expanding rocket nozzle kind of field. And I want to point out a couple of things. This is the Mach number here. Assume it came out of the vent at Mach 1 and accelerates out to Mach 3 before going through this shock wave that slows the fluid back down. And the pressure, which is the second row of numbers, and you probably can't read them, but you don't have to, is the ratio of the pressure to the pressure inside the starting point in the nozzle. And it decreases, and in this stippled zone, it actually gets less than atmospheric pressure. So it's almost a vacuum. We don't know in magnitude, but the car I showed you was sort of in this region, and the windows on that car blew out. They didn't blow in. And that's maybe anecdotal evidence that the pressure outside the car was lower than the pressure inside. Not a very rigorous conclusion. So this is just a general map. When I scale it up to Mount St. Helens dimensions, and there's no fudge factors in here, I just scale this up to be an event longer in diameter as we measured at the mountain. And when I superimpose that on my map of the blast zone that I showed you earlier, the direct blast zone corresponds to this supersonic zone in front of the Mach disk shock. And so that was my belief that this part of the flow, gravity is not important. It's the expansion of the gases that are driving that. And then when the flow goes through the Mach disk shock, it slows down, gravity takes over, and the flow follows. Well, using this rocket nozzle theory, I was then able to compare the lateral blast to a Saturn V rocket. And I'll just conclude by showing you a couple of the numbers about energy. I love to give this talk at JPL because Mount St. Helens makes rockets look pretty puny. And that's because the area of the vent is enormous. It's 4 orders of magnitude greater than the area of a Saturn V rocket nozzle. The mass flux is enormous in Mount St. Helens because we have this rock-laden gas coming out, whereas rockets use hot gases that are very low density. And all of this adds together to me to imply that Mount St. Helens had 5 orders of magnitude more thrust than a Saturn V rocket nozzle. And this thrust was actually measured by seismometers, and it agrees very well with calculations. There is a problem that has persisted for 24 years, and that is that the seismic measurements indicate that the lateral blast was dominantly vertical, not lateral, like the pictures suggest. And that is still a top controversy. And then I could calculate the total energy of the blast, 24 megatons. 7 megatons of that was propagated, was dissipated as the blast traveled over the land. It was converted into kinetic energy. But 17 megatons was retained as heat in the ejecta. And if you walked around there and broke through the crust, it was hot. And it's heat because it buried all of those trees with volcanic ash that was hot, and the trees burned in a reducing environment. And I'll tell you, that was so stinky that everybody had to throw away all the clothes they wore and make field work out there because it was a pretty hostile environment, and also very rich in carbon monoxide, so it wasn't good to be downwind of those trees. So volcanic events that kept happening. I got to a point where I just was saying, please, no more volcanoes. I want to finish my Old Faithful studies. I got to apply my geyser theory quite prematurely to volcanic eruptions, and it's really been a lot of fun, and it does involve a lot of physics and math, so I'm delighted that I can share that with you today. Thank you.
Thank you very much. We've got some time for some questions.
The first volcano that you were talking about that shoots the smoke rings, what was the name of that one?
Reventador.
You mentioned one right before you mentioned Reventador.
Oh, Etna.
Etna, where is that located?
It's in Italy.
Italy?
If you call up smoke rings plus volcano on the web, you'll find Etna. And the other two I mentioned were ASO in Japan, and Stromboli, which is in Italy. I found one smoke ring each for those.
Are those rather common before an eruption, or?
They've been reported anecdotally. I found a report as early as the late 1800s. Some explorer reported them on an island off of Italy that I didn't recognize. These from Etna were common in one eruption, maybe in 2000 or something.
Oh, so they're not like on a schedule?
No, they're not common. They're more curiosities. They were easy to photograph, though, because they lasted for 10 minutes. And one clever guy on the web managed to get one positioned over his head so it looks like a halo. Yeah.
So basically, at the mouse and Kells, you have a cloud that's moving at supersonic speeds. Is that correct? So is that something that's actually common, or is mouse and Kells unique in that respect?
Now, I spared you a kind of dry lecture, but I have to bring it up here. Mount St. Helens was not supersonic with respect to air, like you think of an airplane. So you didn't hear sonic booms. When you have a fluid that's full of dust, it has very low sound speed. And one way you can think of it is that sound speed is proportional to the molecular weight of the gas. So hydrogen has a very high sound speed, helium has a high sound speed, nitrogen is lower, freon is lower, dusty gas is like a high molecular weight gas. So the sound speed of that fluid at St. Helens, I estimated, I calculated, if it was a homogeneous dusty gas and didn't have flying tree trunks and everything, it was about 100 meters a second. So when I said it was going Mach 3, that would be 3 times 100 meters a second, 300 meters a second, inside. So it's internally supersonic. And we're starting to think that quite a few volcanoes are internally supersonic, and that's an emerging field of volcanology because that compressibility term has been ignored in the literature because it was just too hard to do the mechanics. If you could take fluid mechanics and rewind it a century with supercomputers, you would find it to be a different science. But because the momentum equation was really difficult to solve with compressibility and gravity, fluid mechanics split into two fields. The field that dropped gravity became aeronautics, the field that dropped compressibility became hydraulics. And the sciences have really followed that split. So in geology, we tend to learn about hydraulics because of the way rivers flow. But compressibility now can be handled with supercomputers. And so the model we're doing with the rocket probe will have both gravity and compressibility. And it'll be three-dimensional too. That's a good question. Yes?
I have a two-part question. The period of your model volcano was approximately 5 minutes. What did you do with that model to change that periodicity? And why do you think Old Faithful
Why do I think? Oh, well, we could plug the other plug in and heat it up faster, and it would erupt every 2 minutes. I think I've been.
The volume of water would make a difference.
It would. Yeah. This is filled up. If you tiptoe down here, you don't want to get burned. But it's, yeah, there's a joke one day, and they had a wheel, like from a fire engine or something. Just before the eruption, they came out, planted in the ground, started turning. My hypothesis is that Old Faithful is, the intervals are lengthening because of about 3 earthquakes over the past lengthening, and I think those earthquakes fracture some more longer to heat that up. The heat for Old Faithful, ultimately, it's underneath Yellowstone. You know, that's 100,000 years overdue for eruption, and they're watching it very carefully. Because we don't know what the precursor is for an eruption. It happens every 500,000 years. It's hard to imagine an earthquake could supply of hot water because it goes down quite deep. But it's easy to change the cold water, and you can observe that in other geysers around responding to earthquakes. There was an earthquake about 3 miles, maybe 50 kilometers from Old Faithful, and 12 days later changed dramatically. The Hebgen Lake earthquake in, it was 1956, changed a lot of the geysers, almost instantly. And there was just an article published that some of the geysers in Yellowstone responded to an Alaskan earthquake. So this whole field of long-distance interaction, quite an interesting area. Yeah.
I have to excuse my physics ignorance, but with the pressure that builds up before the eruption, is there something blocking the valve while it builds up, or?
No, and that's one reason it's intriguing. Old Faithful is almost the opposite of this geyser. The boiling curve of water depends on the pressure. Up to 7,000 feet at Old Faithful, the boiling temperature is only 93 degrees. The column of Old Faithful, going down, I've probed it to 70 feet with the temperature. The boiling temperature increases because of the pressure to about 124 degrees at the base. But Old Faithful never gets to be quite that hot. The column heats up, and when it splashes, like you saw in the early part of the video, the water, if the water's up, it comes back down. It doesn't change the tree stump. It unloads the column. And this is the water's hotter than 93 degrees, it just keeps going. It cascades downward. So there's no blockage. Now, in a volcano, you do have a crust, usually, that is capping it. And the pressure does have to build up enough to basically be higher than the tensile strength of the rock. And that is a very significant pressure. It's tens
How
of...
far down was that camera? Did you end up with the camera?
Yeah, we didn't do a good job narrating it. The camera went down and looked at 40 feet. We couldn't get in fast enough after eruptions to get down to the full 70 feet that we've gone.
That's as far down as it goes. So.
The furthest anybody's probed it is 70 feet. A guy named John Reinhardt claimed that it went down 200 meters, but everybody thinks he just piled up cable on the bottom because you can't tell. When we were on the ledge one time, we kept feeding cable in. And then Jim recognized that we were stuck, and he yelled at us and we pulled it back up. So I've never lost anything in Old Faithful, permanently. I did have a problem the very first time I probed it. I was using plaster of Paris anchors because I didn't want to use a lead weight. And of course it's very brittle. And so my first anchor just broke. And the field solution was I tied a sock on my next anchor to plaster together. And the sock came off in the conduit. Oh my gosh. Well, a month later, I got mailed by the park ranger a petrified sock. Old Faithful just blew it out onto the surface and it sat there. And he had a little bow tied up.
I have a question. 24 megatons was the Mount St. Helens. Can you put that in any context for us?
What was Hiroshima? 30 kilotons? Jeremiah? 15 kilotons.
15
Kilotons. So it's a factor of 1,000 more than Hiroshima. And I don't like using megatons because volcanoes aren't like bombs, but it's just inevitable that people think in that terminology instead of in joules or... Yeah.
On your diagram of the blast, you have directly in front of the blast the boundary between the supersonic flow and I guess the subsonic flow is this Mach disk shock, which in looking at the previous slide of the rocket nozzle, it seemed to make sense to me that, well, okay, there's the disk and it's here's this conduit from the rocket nozzle, and the disk spans that nozzle, and the nozzle itself forms the remaining boundary. But in the open air situation, you still have that disk, and I don't know what really defines the boundary on the sides.
Oh, actually, the rocket plume was outside the nozzle.
It was outside.
And the boundary is simply the boundary condition with air, the 1 bar isobar, or whatever the pressure is. If you see a rocket launch, they try to optimize the design of the rocket nozzle to get the most thrust, but they can't. And that design depends on the pressure ratio of the firing to the atmosphere. But as the rocket goes up in the atmosphere, the pressure changes in the atmosphere. And if you watch a shuttle launch, you'll see that the plume just getting broader and broader as the atmospheric pressure gets lower. And so they have to design these to be the most efficient at the optimum pressure ratio. We had a speaker in geology yesterday who was using GIS, the GPS, Global Positioning Satellite, for his work. And he has a station in Bermuda, and when the shuttle goes over it, the shock wave from the shuttle compresses the ionosphere, and that affects the GPS readings. They've actually measured the shuttle passages with the GPS systems. It was a really fun dinner conversation.
Maybe one more question, and one over here.
Well, I just wanted to know if you could compare the energy release at Mount St. Helens to other volcanoes. Was it a little one or a really big one?
It's, in the geologic time scale, it was a minute one. There are volcanic deposits. Okay, Mount St. Helens erupted about a cubic kilometer of material, and there are volcanoes, they're extinct, but in Nevada, in which there have been 1,000 to 10,000 cubic kilometers of ejecta. And if Yellowstone erupts, it'll be probably 1,000. It would be a catastrophic eruption. And there are volcanoes capable, that are alive, that are capable of these big eruptions. But the recurrence interval is longer for the bigger eruptions, too. But it's really fun to discuss with a bunch of volcanologists and pass around the microphone and say, well, what's the precursor of a 500,000-year event? You know, is it going to take, I mean, maybe Yellowstone is the precursor. It's erupted 3 times at about 500,000-year intervals, and it's been 600,000 years since the last one.
So, great questions, everybody. I think Sue would be more than happy to stay down here. If you have some more questions, you can come down front and speak with her. If you want to play with some smoke rings, feel free to come down and play with some smoke rings. Let's thank Sue again for